So a planet in an orbit is a motion of 6 variables. You have 3 components of position and 3 components of velocity. We need therefore 6 constants to be able to integrate the motion. So far, we identified only one, the magnitude of the angular momentum vector, which we use to show Kepler's 3 laws. Let us see what other quantities are found to be constant so we can integrate the motion. First one should be the angular momentum. If we recall again that it is a vector, is the cross product of the position times the velocity, which is perpendicular to the position vector and to the linear momentum. So let's take the time derivative of this. It becomes then the time derivative of L is equal to r dot cross r dot plus r cross r two dots. The first term zeros because it is a cross product of a vector with itself. The acceleration, r dot dot, is given by the equation of motion. Again, you have r cross r, so cross product of a vector with itself, so that cancels. So not only the magnitude, but the 3 components of the angular momentum vector are conserved. So that gives 3 constants of motion. Another conclusion that we can draw from that is that because the angular momentum vector is fixed and perpendicular to the position vector, then the motion is restricted to a plane perpendicular to the angular momentum. As you can imagine, another constant of motion is going to be the energy. Let's consider the dot product of the velocity and the acceleration. If we substitute the equation for the velocity and for the acceleration use the gravitational force, this expression becomes, so you can ignore the phi hat, that becomes minus mu r dot over r squared. And this is the derivative of 1 over r. Yet we can also write r dot dotted with r two dots as the derivative of r dot squared, which is then the kinetic energy. Now, if you equate these two expressions, we find that the derivative of the kinetic energy minus mu over r is equal to 0. So we found another constant of motion. And this is, of course, the energy. We have now 4 constants of motion. The last one should be the eccentricity vector, which is also called the Runge-Lenz vector. Now for that, consider the vector product of the angular momentum and the acceleration. The angular momentum is the radius vector crossed with the velocity, and the acceleration is the gravitational force. So if you take this triple product, and if you use the vector identity that A cross B cross C is equal to back minus cab, you can rewrite this triple product. This is r squared r dot vector. Let me explicitly write the vector here so it becomes clear. I'll divide all terms by r cubed. This is equal to the derivative of r vector over r. R vector over r is r hat. Now, because the angular momentum is a constant, you can also write that L cross r dot dot is equal to the time derivative of L cross r dot. Now, if you equate both equations, we find that the time derivative of L cross r dot plus mu r hat is equal to 0. So we found another constant of motion. It's not the most transparent vector, but at least one property is immediate. It lies on the plane of motion. You can see that because if you see the first term, L cross R dot, L is perpendicular to the plane of motion. R dot is tangential to the plane of motion. So if you take the cross product, you have something that lies on the plane of motion. As for the second term, it's dependent on the radial unit vector, so obviously it's also on the plane of motion. So the whole vector is in the plane of motion. So we can say so far only that this is some vector that lies in the plane of motion. Now we can also find the direction, and we're going to find out that this is a vector that points towards perihelion, and it has magnitude equal to the eccentricity. Let's find out how we can arrive at this conclusion. Let's take the dot product of this vector, let's call it big A, with the radius vector. So r dot A by definition is r times A times cosine of theta, where theta is the angle between them. Substituting for the definition of A, this is r dot L cross r dot plus mu r dot r hat. So the first term is a triple scalar product, and you can use the identities A dot B cross C is equal to B dot C cross A, which is equal to C dot A cross B. So you can use this to write R dot L cross R dot is equal to L dot R dot cross R. And because the angular momentum is R cross R dot, this is equal to minus L squared, and it's a constant. So we have that R dot A is equal to minus L squared plus mu times R. Now if you equate this equation with this equation, and then you solve for R, now this looks a lot like the equation of the orbit. Just like before, the square of the angular momentum over mu is equal to A times 1 minus E squared. But now we have that big A over U is equal to minus E. A was the amplitude of this vector, and theta is equal to phi. So it is oriented such that the angle that this vector makes with the position vector, with the radius vector, is the true anomaly. So the conclusion is that this is a vector that is parallel to the line of apsides, pointing to the direction of periastron. So it doesn't matter where you are in the orbit, this vector seems to know where periastron is. A profound implication of this is that the direction of perihelion, and thus the line of apsides, is fixed. The orbit does not change its spatial orientation. Now, if this is the vector A, and this is the amplitude proportional to the eccentricity, we can define a vector that has amplitude equal to the eccentricity. Let's call it the eccentricity vector. The eccentricity vector points towards perihelion, has magnitude equal to the eccentricity, it lies on the orbital plane, and it is constant. So it seems that we found several quantities. Found the angular momentum, we found the energy, and we found the eccentricity vector. Altogether, these are 7 quantities. So it seems at first that we are overspecified, but because the eccentricity vector depends on the angular momentum, some of these quantities depend on each other, and we end up with 6 constants in the end.